So we continue our morning session, and with pleasure, I introduce our next speaker, Ioannis Diamantis, and he will speak about new combinatorial invariants of doubly periodic tangles.
Thank you so much. Thank you. So first of all, let me thank you for inviting me to give this to present my work here. It's a great honor, especially during these very difficult times. So as you said, my name is Ioannis Diamantis, and I'm going to talk to you about new combinatorial invariants of doubly periodic tangles. And I'm going to give you the motivation and the whole story behind these double periodic tangles and, in general, periodic boundary conditions uh, in order to understand that there is almost none mathematical study behind this. So it's a very new topic. This is a joint work with Professor Sofia Labropoulou from the National Technical University of Athens and Dr. Sonia Mahmoudi from Tohoku University. So let's start by defining a little bit what double periodic tangles are, which from now on I will refer to as DP tangles, right? Double periodic tangles. So double periodic tangles are nothing but entanglements of curves that are embedded in the thickened plane and that they are periodically repeated in two transversal directions. They are very, very, very important in the study of systems, in general, physical systems, since their properties are associated to the physical properties of the systems. For example, elasticity, energy even, and other things. So a better understanding of the geometry and the topology of these objects will give us a better understanding of their physical properties in general. That's what we believe. And the most important thing, at least for me, is that there is no universal mathematical study, and there are many, many open questions when it comes to double periodic tangles. So if you're familiar with knot theory, very standard and basic knot theory, what we will try to do is borrow tools from knot theory and try to extend these tools to study DP tangles, as we call them. All right, and where do we find applications of these DP tangles? In general, we find them in entanglement of filaments, which means it can refer to various phenomena, depending on the context, such as polymer melts, fabric-like structures, molecular chemistry, cosmic filaments, and more, right? These are just some examples which are very, very, very important. And our approach so far corresponds to all of them. So we want to have like a universal mathematical language to study DP tangles. And that's what we started doing last year. And we were impressed by how many things were not known about these DP tangles. Okay, so let's give the proper definition so that we can understand a little bit how they work and what they are. We start by considering diagrams of links in the surface of the torus. All right, so imagine that you have the donut shape and you have links on the surface of the torus. So we're not considering the solid torus, just the surface. Okay, to obtain information about possible crossings that there are on the surface, we consider the thickening of the torus, and we see something like the picture that you see here, the figure that you see here. So we have the torus, right? And we consider its thickening. So now we can have like positive or negative crossings. We can know which strand goes above and which strand goes below another strand. So a DP tangle, we start by a link in the thickened torus, and a DP tangle is nothing but the lift of that link under the covering map, right? So we consider the universal cover, and what we have actually is what we call tau infinity or a DP tangle. All right, and if we project this on the plane, then we have the diagram, a link diagram. We guess double periodic diagram, let's say, or DP diagram. And from now on, we will refer to these things as motifs. I'm going to explain how important these are. Let me show you a motif. So the representation of a motif on a flat torus will be called a flat motif. So what is a flat torus? I just cut open the torus and I have the identification space. And I realize that I can represent my links in the thickened torus as links as flat motifs. All right, considering, of course, that parallel boundaries of the parallelogram will be glued together, and you can have the thickened torus in that way. All right, so this is extremely important for me because what I will try to do, and what we are trying to do, is try to find the smallest possible flat motif representation that will generate the whole deep rectangle, that will generate the deep rectangle. All right, and this is, I'm sorry, and this is what we will call later on a minimal motif. And here is the picture so that we can see the whole thing. So we start with a link in the thickened torus that we call motif, right? And if we take the identification, if we open the thickened torus, we have what we call flat motif, and this master here on the right is a deep rectangle. So it's the under the universal cover, it's the lift under the universal cover. So we are talking about infinitely many lines that extend to all directions, and this link, this motif, would correspond to this deep rectangle.
May,
Okay.
may I ask the question? So in this square, you consider a diagram of a knot, yes?
Yes.
So it is flat. So before that torus is a thickened torus, and now
Correct.
you consider a flat situation, but no, the
Correct.
diagram. Okay.
And I keep track of the information that I have, all the crossings that I have, right? So it's a classical diagram. You're right. It's not thickened. Of course, you can consider it as a thickening, and you can have like the same thing, right? But it's better to see it like flat to make things a little bit easier and simpler. Okay, so the next thing now is the following. We want to understand a little bit how deep rectangles are related one to the other. So we want to understand how isotopy or equivalence, if you want, can be translated in terms of the diagrams, moves on the diagrams. And in general, we can easily see that the topological classification of deep rectangles is harder, I should say, um, when it comes to the problem of the classical classification of knots and links in 3 space. This is much harder. Why? Because all the moves that need to introduced here for the equivalence needs to respect double periodicity, right? The periodicity. So in classical knot theory, you can do some standard Reidemeister moves, and that's all, the 3 Reidemeister moves plus the planar isotopy, or delta moves, as we call them. But here, things are a little bit trickier. We have to take into consideration the periodicity, and we have to take into consideration other moves that are allowed, for example, rigid transformations of the plane, and other things that play an important role. So we will use we will use tools from knot theory plus standard tools from linear algebra to try to understand a little bit how equivalence will look like in terms of moves on the diagrams. All right. And what we know so far is the following. Whenever someone wants to classify topological objects, we create invariants, right? Topological invariants. The most famous one is the Jones polynomial for classical knots, and we're wondering whether we can do something like that for deep rectangles. The answer is yes, and it is already being done by Grizanov, I think around 20 years ago, 18 years ago. The problem is that all these invariants are based on assumptions when it comes to minimal motifs, minimal flat motifs. So the square that you would have to identify its boundaries, you consider it to be minimal. And minimal means the smallest possible diagram that can create the same deep rectangle. I'm going to show you some examples to understand this issue. But that is a little bit weird when it comes to mathematics because we start already by assuming that we have a minimal motif. So in practice, this is not very helpful because if you give me a motif, how would I know that it is minimal? Because if it's not, I cannot compute the topological invariance that we know so far. So this is a very interesting question, and that is our aim, to try to understand how to obtain a minimal motif, given any flat motif, given any motif, try to understand when we have a minimal motif, so that we can, first of all, apply the standard topological invariance that we already know, and of course, extend to more complicated invariants and try to understand whether there's an algebraic structure behind it, and we can have like the Hecke algebras on temporally algebras in the classical knot theory category, and try to understand whether we have something like that to enrich this theory even further. Okay, so if you observe here this figure, you will see immediately that these 4 flat motifs give rise to the same deep rectangle. So what is a deep rectangle? I just have to repeat it to make sure that you have it in your mind. Just consider the universal cover. All right, so consider copies of these things, right, and put one above the other, to the left, to the right, below, and assume that they go, you have infinitely many. All right, so you can see that the second one, right, or if you want, the first one is like a stretch of the second one, right? So there shouldn't be any difference in the universal cover. The third one is what I call scale equivalent to the second one, which means like two copies, right, of the second one. You put one above the other and you have this, right? And the third one, and the fourth one is just a contraction. So what does that mean? Why is that important? Because this gives, we have to keep in mind that there is always a lattice involved, right? There is always a lattice. So let me remind you a little bit about the lattices. What we actually have here is a periodic lattice. Each d rectangle comes equipped, let's say, with a periodic lattice. And that periodic lattice is the classical lattice that we learn in linear algebra, and different bases for the plane will give rise to equivalent, right, double periodic tangles. And here you can see the UV, the blue one, right, the classical basis, and the UV prime, the green one, if I see correctly, and you see it's just a sharing. All right, so we have to keep in mind that we will always assume from now on a fixed lattice, right, so that we can actually define mathematically scale equivalence, stretching, and shearing, and all these beautiful concepts that we will introduce in a minute in a more rigorous mathematical way. So any questions so far? No? Okay.
No.
Okay, great. Great. So these are very, very, very important and new things, and I really hope that I can communicate it in a way that it is interesting also to you. Um, so, okay, I will continue. To save some time, I will not go into details when it comes to minimal lattice, but I want you to keep in mind that there is always a lattice involved, right? And there is a lattice that includes all other lattices, and that's what I will call from now on a minimal lattice. And it will be fixed. It's like, as I say here, it's like a grid that accommodates a DP rectangle and a minimal motif, right? Is minimal for generating this DP diagram. Okay, now, in order to study DP equivalence, we realize immediately that there are two different categories, let's say, of moves. The first one is what we call local motif isotopies. So isotopies moves that take place very locally, and this involves the standard Reidemeister moves that we know from knot theory. I'm going to remind you in a minute, plus surface isotopies, because we shouldn't forget that we are on the thickened torus, right? So we are on the surface of the torus and consider the thickening. So there, other things might occur which are more interesting compared to the three sphere. And also, we have what we call global isotopies, which of course involve affine transformations of the plane, right? Invertible affine transformations of the plane, and what we call rescalings, okay? Which I will show you in a minute. I will show you some pictures in a minute. So let's study first the local motif isotopies. Let's try to understand them, and then we will continue with the global ones. So the local motif isotopies, just imagine that you have like a link on the thickened torus, right? And this link, a strand moves. So if you take the diagram, right, the projection of that link, then the diagrams would be equivalent, right, under these four moves. The standard three Reidemeister moves, where you see the first one is just a positive or a negative kink. The second one is like you have two strands and you can consider doing this move, right? And the third one is just a strand which goes to the other side of the crossing. So these are the classical three Reidemeister moves that are allowed, and they take place away from the meridian and longitude of the thickened torus. What longitude and what meridian? The ones that you will choose to cut, right? The ones that you will choose to cut your thickened torus in order to obtain your flat motif, the flat motif diagram, right? So the identification space. And also don't forget that we also have the planar, the delta move, right? Where you just make turn like a strand into this curly stuff. All right, so that's the first thing, which is straightforward, and that's something that we expected. But there are many things that are not different, but there are some things that are different from classical knots. For example, as you can see here, I have a motif, right? And I do a Reidemeister 2 move here. So this strand, right, goes here. This will follow in the universal cover everywhere. Okay, so that it's what I mentioned before when I said we need to respect the periodicity of the DB tangle. So all the moves that we will introduce somehow need to respect the periodicity. And when I say local motif isotopies, and we said like they take place away from the meridian and longitude, it means that they take place inside the identification plane, inside this parallelogram. All right, you can see here. So we are not allowed to touch the boundaries, the meridian or the longitude. Okay, so far these would be different types of moves. Okay, so this is quite interesting. And if you want to keep in mind how these things look like, just imagine that you are here and you are walking, right, that way. Once you reach at this boundary, you glue with this one, so you are here. And when you reach at this point here, you are here. All right, so that's an easy way to remember how these things work. Just imagine that you walk, and this is the path that you're walking on, and it's glued. All right, so these are the Reidemeister moves. Local motif isotopies, they take place inside. Okay, what happens to surface isotopies now? What are surface isotopies here? So surface isotopies are kind of straightforward. Number one, we need to remember that there are 4 types, or 5 actually. All right, but all of them are the same philosophy. Just think of a strand, right, which lies inside the interior, right? It's in the interior of your motif, right? And then you allow some moves, for example, the planar, right, the delta move, and the resulting arc remains inside the motif. Okay? Or you can have something else. You can touch a boundary, longitude or meridian, doesn't matter. Right? So before the move is applied, you do not touch the boundaries, but after you apply the move, now you touch the boundaries. And you can see how the second, the figure in the middle becomes like the figure in the right, in the bottom right. So this cross here corresponds to longitude and meridian, right? One is the longitude, the other is the meridian. And this is what we will see if we just push this towards this point. It's like a finger move. You just push it, push it, push it. So because of the identification space, it goes to the other side. So you can imagine you push this, right? It goes here, it touches this boundary, and it goes to the other side, and it appears like this. So this is what we call surface isotopy. And we are almost done. We need 3 more moves of this type that are straightforward. One is when you already touch one boundary, right? And then after the performance of the moves, you might touch 2 boundaries. So here you touch one boundary, you can see how it looks like. And then you perform delta moves. So it's like, again, the finger move, as I like to call it. You can see how it works here. And then if you push it this further and you cross this, you can see it goes here, right? And then it goes up here and back to its initial position. So there are moves that take place in the interior, there are moves that take place in the interior, but after the performance of the move, you touch one of the 2 boundaries. And there are moves that after the performance, you touch both boundaries. Okay, and we have to keep in mind these tricks because these make things a little bit more complicated. These examples that I have here are very straightforward, right? But you can imagine how complicated examples you might have because you can imagine very difficult patterns, very different and complicated DP tangles. All right. And finally, we have to also consider what happens when a crossing passes through one boundary, and we have to keep this in mind, right? That the crossing can pass through a boundary. So why am I showing you this? Because I'm trying to understand a little bit the equivalence, and this is completely new. All right. So we kind of knew, right? But there is no mathematical study behind. And the proof is actually based on a classical three-manifold topology where we convert all these diplytangles into mixed links that are like Kirby links, Kirby link diagrams of knots to represent 3 manifolds. And then we take advantage of the classical theory that we know, and we just translate the moves here. Okay, so that's why I was showing you all these things. And finally, we have to keep in mind that we have the torus rescalings, as we said before, contractions or stretches, right, which are induced by various rescaling isotopies, let's say, of the supporting torus. And of course, we have to keep in mind that always the lattice is also, it could be affected also by these moves. Now, let me go straight forward to the affine transformations of the place because I see above the plane because I want to have like 10 more minutes to show you, to talk to you about something even more interesting, like invariance of these DP tangles. We also include classical affine transformations of the plane, rescaling, rigid translation, rigid rotation, you can see here, and shearing transformation, right? And any other affine transformation is generated by these elementary transformations. So if we take the classical local motif isotopies, we also include surface isotopies and affine transformations of the plane. Do we have equivalence? The answer is no. We still need one extra move, which is called a dent twist. And what is a dent twist? A dent twist is just like twisting, right, the torus, the surface of the torus, along a specific curve. Usually for us, it would be a meridian or a longitude. So you see here, this is a meridional twist. So you take the torus and you just keep this fixed and you twist one of the two torus and you keep them glued together, or longitudinal, which I cannot easily draw or explain using my hands. All right. So if we involve all these things, then we have what we call den equivalence. Sorry, we have DP tangle equivalence. And this is the main result of the talk so far, where we prove that DP tangle equivalence is actually corresponds to the moves that I just introduced. So local motif, global motif isotopies, which correspond to also torus rescalings, dent twists, surface isotopies, and all affine transformations of the plane. So that is the first part. We now have the equivalence, right, between DP tangles. What would be the next step? The next step would be to try to create, to construct invariance. Do we have invariance? As I mentioned before, we do. So Grizanov, Meshkov, and Olmelchenko in 2007, almost 20 years ago, they constructed the classical bracket polynomial. If you're familiar with the classical bracket polynomial, you just destroy, kill its crossing, right, by smoothing of this type or of this type, and you keep track of what kind of how you kill the crossing using the type A smoothing or the type B, and then you take a sum over all states that you will obtain in the end of the diagram. So this polynomial, it turns out to remain invariant for DP tangles, but what is the problem? The problem is that it doesn't capture, first of all, it requires a minimal motif because it doesn't capture dent twists. So it is not invariant under dent twists. It's an invariant under motif isotopies for a fixed point lattice, but it fails to be an invariant for dent twists, which means that for equivalent DP tangles that differ by a dent twist, this most likely will fail to distinguish or have like an idea that they are the same. And this pair that you see here, these numbers M and N, correspond to the number of windings around the meridian and around the longitude. So it's like an MN torus knot. Okay, so because of this, and because we want to construct an invariant for DP tangles that also remains invariant under dent twists, we started by trying to understand a little bit what's going on. And we also extended these results that I just mentioned to other types of diagrammatic settings, let's say other diagrammatic settings, such as virtual knots or virtual DP tangles, if you want, singulars, pseudo, tied, bonded, and of course my favorite for knotoids and linkoids. So we have the same theory, right, for DP tangloids, as we call them. And we also constructed the Kaufman bracket polynomial for DP tangloids, which is almost the same as Grizanov, but we did it in a little bit slightly different way, which is a little bit, it has a more geometric flavor. Anyway, I don't think that I will reach at that point, but I'm just mentioning. Okay, so let's see something a little bit more interesting. Let's see, I still have like time. Okay, yes. So let's see our motivation to construct invariance and what kind of invariance will we construct. We will start by constructing what we call directional invariance. I will come to that in a minute. What is a directional invariant? But before that, let me explain a little bit the motivation behind this. Because as I said, there is no mathematical study right? Rigorous and universal mathematical study of these monsters. So we wanted to understand slowly what is going on. So here in this figure, I show you two different dipitangles. Well, different, we don't know, right? So we see two dipitangles, or two motifs, correct? And the universal covers the dipitangle. And we're wondering whether we can distinguish these two by the types of the curves that they involve. So you can see that this thing here on the left is the figure 8. And if instead of isotropy, one uses homotopy, we immediately obtain the anode. So this is a null homotopic curve, right, which means contractible to a point in the interior of the motif. While if we try to do exactly the same thing on the other motif, we realize immediately that this fails. All right. Why? Because these monsters here touch the boundaries, which means they form essential curves that you cannot kill, either go around the meridian or around the longitude. So you cannot, they are not null homotopic, not contractible to a point in the interior. These are essential curves. All right. So with this in mind, we are ready to have, we try to understand a little bit the difference between motifs or dipitangles that involve null homotopic components and those that involve essential components. And what kind of essential components? It's self-explained, I guess, that we will obtain an invariant. The question is how good that invariant will be. Will that be strong enough? Okay, so to do that, we first define what we call interlink compounds. And why is this crucial? As you can see in these figures, right, you can see that this is just one knot. So you can see it's very complicated, right? And this figure in the middle, for example, is just one knot. It goes here, then we are here, we are here, then it goes up, we are here, and we reach the initial position. So, and we see that it touches both boundaries, right? So yes, this is essential, and we realize immediately that it's not only around the meridian, it's not only around the longitude, it's both. So this is very, very complicated. While this one on the right, although it's not a knot, but maybe many, it's very complicated. They are interlinked in a very complicated way. And on the left, I think that we have a knot. If I remember correctly, this is also a knot, the leftmost figure. So we said that in order to understand how motifs behave, we need to first understand separately each and every component of theirs. All right, so we define what we call interlink compound to be a link that can be a sublink, sorry, of the motif that can be somehow split from the rest, or maybe not, right? But now using only isotopy. And what does it mean, maybe not? For example, in the middle, right, there's nothing we can do to split it. So the whole thing is a compound, an interlink compound. While here, I can see immediately that there is something I can do. No, it could be, no, it's very complicated. All right, this is very complicated. I thought that it goes like this in the beginning, but then I realized that it goes like this. So it's a very complicated motif. Have to zoom in and see a little bit the details. Okay, now in this figure, in the topmost figure, you can see a two interlinked compound flat motif, right? So one is the gray, and the other one is the trefoil knot together with the unknot. So this is one compound. Okay, don't forget here I am using isotopy, so I can just take the whole thing and put it inside a 3-ball. All right, and that means that I can isolate it from the rest. That's very essential, very crucial for us. While this one here, this compound here, I cannot achieve that. There is no ball that can fit the whole thing, but there is a ribbon that can fit the whole thing, right? So immediately I understand that I have different types, different classes of interlinked compounds, and these classes actually form invariants. And the last two figures, you can see examples of flat motifs with 3 interlinked compounds. So you can see here we have this gray, this black, and this gray, which is also extremely interesting because it's the chain link, right? And here we have a monster. We have this small trefoil here as a second one. I'm sorry. And we also have this chain link here. So 3 compounds. The rest is an interlinked compound on its own. So starting from interlinked compounds, the next thing is to define um, let's say the classes. And I've already explained, if you can have a compound and you can take this compound and put it inside a three ball, right? Then you can assume, not assume, sorry, then you can guarantee that this is a null homotopic compound. This is a compound that can be shrink to a point, contracted to a point. But if this is not the case and you can put it in a ribbon, right? Then you will call this, we will call this a ribbon compound. And if a compound, it's not a ribbon and it's not a null homotopic, then we will call it a cover compound because it covers the whole thing. And these are some examples of cover compounds, with my favorite being the first one, because you can see two ribbon compounds, right? Interlinked, so they are not ribbon anymore because they are interlinked here, and there is nothing you can do so that you can distinguish them. You can split them using isotopy. I'm not allowed to use homotopy. I'm just using isotopy, trying to separate them, trying to split them. Okay, and we reach at a beautiful, I would call it theorem, not proposition, that says that the class of an interlinked compound as null homotopic ribbon or cover, we also have an ordering relation that a null homotopic is weaker than a ribbon, which is also weaker than a cover. This is important for the proofs. This is invariant under motif equivalence. Right? And motif equivalence means also then twists, means also rigid transformations of the plane, local or surface isotopies, everything. And here are three beautiful examples where you can see that the crossing number is the same. So the crossing number cannot distinguish these three flat motifs. The number of components is the same. So that is also not an invariant, but the class that we have distinguish at least one from the others. So this is a ribbon while these two are covers. Okay, so we immediately see that our invariant is good, right? Because it distinguishes something that the classical numerical invariants cannot, but not good enough because the first two are both covered, right? Compounds, and they cannot be distinguished by this class. So the next thing we did is we went to details and we understood subclasses. I will not talk about subclasses at all. What I want to talk to you about is the following, the idea of the whole thing, which works as follows. In order to create, because I don't have much time, so I want to, in order to create an invariant, one has to do the following. Count the number of arcs, count the number of arcs involved in a flat motif. This is called density. A density is not invariant, right? But using the density, the concept of density, the number of arcs inside the minimal, or inside the motif, sorry, then using this, one can identify and can construct an invariant using this concept of density, and that invariant is very strong. How strong is it? That's a different story. Not strong enough again, but stronger than all the invariants that we know so far. So at least as far as I'm concerned, and from all the literature that I have studied, I haven't seen a stronger invariant than this. And so I will skip most of the things, I think, because we only have like 5 minutes. I don't want to waste your time in case you have questions. So I think that I should stop here. So thank you so much for listening.